There's a place on Earth where two oceans collide, but never mix. A razor-sharp line slices through the sea, splitting it in half. On one side, a rich dark blue, on the other, a murky, almost milky green. It looks unnatural, like someone photoshopped reality. But here's what will blow your mind. It's not fake. It's not a trick. And it's not just one spot on the planet. It's happening in multiple places right now. But what exactly is going on? Why do these two colossal bodies of water meet, but appear to never mix? Is it because of salt, temperature, pollution? Is it dangerous? Could this divide actually affect marine life or the global climate? Or are we falling for a stunning optical illusion? In this video, we're going to pull back the curtain on one of Earth's most mesmerizing and misunderstood natural phenomena and reveal a truth that's even more shocking than the myth. We'll dive into the heart of this mystery, explore the real science behind it, the locations where it happens, and what's hidden just beneath the surface. From the icy edges of the Gulf of Alaska to the turbulent waters near the Strait of Gibraltar, we'll uncover why oceans seem to clash like titans, yet stay separated like oil and water. And here's the kicker. This isn't just about pretty colors. These ocean boundaries are giant clues, whispering secrets about how our planet works. They're signals of power, chemistry, and motion on a scale almost beyond human imagination. Because sometimes, nature doesn't just surprise us, it leaves us speechless. It all began with a single video clip, a shaky handheld shot from the deck of a boat cruising through the Gulf of Alaska. The camera pans over calm waters, and then, boom, a sharp divide appears, like two different oceans stitched together with an invisible seam. One side is dark and stormy, the other light and silty, and the line between them is unnervingly precise. The video racked up millions of views almost overnight, sparking a digital wildfire. Comments exploded with wild theories. Proof the Earth is flat, one user claimed. Another wrote, "This is where the Pacific and Atlantic Oceans battle for dominance." Some even went biblical, suggesting divine intervention was the only possible explanation. The footage became a digital campfire, a mystery everyone wanted to solve, and it kept spreading. But it wasn't just the Gulf of Alaska. Similar images started popping up from the Strait of Gibraltar, where the Mediterranean Sea meets the Atlantic Ocean. And again in South America, where the Amazon River seems to refuse blending with the Atlantic. The internet quickly dubbed it the place where oceans don't mix. Dozens of clickbait videos followed. Titles like "Scientists Can't Explain This Ocean Wall" and "What They Don't Want You to Know About Ocean Boundaries" flooded YouTube. TikTokers added eerie music, dramatic voiceovers, and captions like "Nature is hiding something." It was mesmerizing, spooky, and hard to look away. And the myth was born. The Pacific and Atlantic Oceans meet, but never ever mix. But is that what's really happening? Before we dive into the truth, we need to separate the footage from the fiction and understand how a natural phenomenon turned into one of the most viral science mysteries of the decade. The idea that the Pacific and Atlantic Oceans never mix sounds like something out of a fantasy novel, and the internet ran with it. Over time, the myth evolved. People began to believe that these oceans were physically repelling each other, like two magnets locked in eternal opposition. Some even suggested there was an invisible wall, a natural force field, holding them apart. It became one of those rare internet stories that felt just plausible enough to believe. Even major media outlets picked it up, often simplifying the science to ride the viral wave. Infographics showed a neat division, and some articles implied that the oceans actively reject one another. It's no surprise the myth stuck. It's visual, it's dramatic, and it sounds like something Mother Nature would do just to mess with us. But here's the truth. The Pacific and Atlantic Oceans absolutely do mix, just not in the way we imagine. What you're seeing in those videos and images isn't a battle, or a wall, or some unsolvable riddle. It's a combination of science, optics, and timing, with just enough mystery to keep the illusion alive. Different bodies of water often carry unique properties: salinity, temperature, density, current direction, even sediment and pollution levels. When they meet, they don't immediately blend like food coloring in water. Instead, they layer and swirl, interacting through a process called stratification. That sharp line you see? It's a temporary boundary, a visual artifact of contrasting water masses meeting under specific conditions. And this phenomenon isn't exclusive to oceans. It happens in rivers, lakes, and even estuaries where freshwater meets saltwater. Scientists call these boundaries interfaces, and they're constantly shifting with tides, winds, and seasons. But when the conditions are right, like during calm weather with minimal wave action, nature paints a line so stark, it looks like something out of a CGI studio. The myth is beautiful, but the science is even more breathtaking. Because the real story isn't that the oceans never mix, it's how, when, and why they do. And once you understand that, the illusion doesn't disappear, it becomes even more fascinating. Now let's dive deeper into that exact science. What causes this invisible line in the first place? What's really happening at the molecular level when two seas collide? To understand why the Pacific and Atlantic Oceans appear to never mix, we need to get deep, not just into the sea, but into the physics and chemistry of water itself. The dramatic lines we see between water bodies come down to a few key concepts: salinity, temperature, density, and flow. These variables shape how water moves, where it goes, and whether it blends or resists blending. Let's start with salinity, the saltiness of water. Different oceans and seas contain different concentrations of salt, depending on factors like evaporation rates, freshwater inflow, and current systems. The Atlantic Ocean, for instance, is generally saltier than the Pacific. Why? Because it receives less rainfall and has more evaporation. It also gets inflows from rivers with higher salinity levels. This difference might seem small, we're talking about a couple of grams per liter, but at the scale of oceans, it creates enormous contrasts in water behavior. Then comes temperature. Warm water is less dense than cold water. The Pacific, being closer to the equator in many areas, often carries warmer surface layers than the cooler, deeper parts of the Atlantic. When these warm and cold layers collide, they resist mixing, because denser cold water tends to sink, while warmer water floats on top. Now combine salinity and temperature, and you get density, arguably the most important factor in ocean separation. Saltier and colder water is denser. When two water bodies with differing densities meet, they create a boundary, not a solid wall, but a gradual gradient. This boundary is called a halocline, change in salinity, a thermocline, change in temperature, or more generally, a pycnocline, change in density. These layers act like invisible sheets between water masses, slowing down mixing dramatically. But the separation isn't absolute. Oceans don't slam into each other like bricks. They flow and slide past one another, mixing gradually. This process is called diffusion, and it happens at both the molecular level and through larger-scale turbulence. However, because diffusion is slow and ocean currents are massive, it can take years or even decades for two adjacent water masses to fully blend, especially in areas where mixing forces are weak. Currents play a major role too. The Atlantic and Pacific are governed by powerful global conveyor belts of water, such as the Gulf Stream, Kuroshio Current, and North Pacific Current. These currents transport heat and salt across the globe. When they converge at ocean boundaries, they can amplify the contrast between water masses. These meeting zones can resemble walls, especially from above, because the differing sediments, temperatures, and salinities scatter sunlight differently. That's why the ocean appears to change color so sharply at these boundaries. Sediments and organic matter add another layer to the story. When massive rivers like the Amazon or Congo empty into the ocean, they dump vast amounts of soil, nutrients, and plant debris into the sea. The result? Murky, brownish water colliding with the cleaner, bluer salt water. The stark visual difference intensifies the illusion that two water bodies are refusing to mix, when really, they're doing so slowly and subtly below the surface. Then there's stratification, the natural layering of water. In places where surface water is much warmer or fresher than the water below, the ocean can form long-lasting layers that resist vertical mixing. One of the most extreme examples is the Black Sea, where deep layers haven't mixed with the surface in hundreds of years. These bottom layers are rich in hydrogen sulfide and completely devoid of oxygen. A result of intense stratification that has locked in those conditions over centuries. So, is there really a barrier between the Pacific and Atlantic Oceans? Scientifically, yes and no. There's no solid wall, but there are fluid boundaries caused by real physical differences. These boundaries resist mixing and create the illusion of separation. While nature eventually erases these lines through turbulence, wind, tides, and deep ocean currents, for a moment, a brief, beautiful moment, the ocean draws a visible line in the water. And here's the kicker. This isn't just a curious quirk of nature. It's part of how Earth regulates its climate, distributes nutrients, and maintains biological life. Without these layers and boundaries, the oceans wouldn't circulate heat properly. Marine ecosystems would collapse. Even our weather systems would change drastically. The next time you see that sharp ocean divide, remember, you're witnessing more than a cool visual trick. You're watching the planet's climate engine in motion, an invisible ballet of salt, heat, and motion that sustains life on Earth as we know it. While the Gulf of Alaska might be the internet's poster child for oceans that don't mix, this stunning phenomenon plays out in multiple locations across the globe, each with its own unique twist on the spectacle. Let's begin with the Strait of Gibraltar, the narrow waterway that connects the Atlantic Ocean to the Mediterranean Sea. Here, a visual divide often forms due to stark contrasts in salinity and temperature. The Mediterranean is much saltier than the Atlantic because of its high evaporation rates and low freshwater inflow. As a result, when these two bodies of water meet, the Mediterranean's denser, saltier water slips beneath the Atlantic's fresher flow, creating visible layering and sometimes a striking separation line. Next, head north to the Baltic Sea, where freshwater from rivers meets the saltier North Sea. This mix creates a persistent halocline, one of the sharpest in any ocean system. Because the Baltic is almost landlocked, it doesn't exchange water easily with the open ocean, leading to long-lasting layers that don't mix well. The result, a natural laboratory for oceanographers, and another location where waters seem to resist blending. Then there's Cape Horn at the southern tip of South America. Here, the Pacific and Atlantic truly crash into one another. Powerful currents from both oceans meet head-on, and while the mixing is far more aggressive, there are still moments, especially during calm seas, when contrasting watercolors are visible in satellite images. These moments showcase the incredible complexity of ocean interactions at one of the roughest maritime crossroads on Earth. A particularly famous example lies at the mouth of the Amazon River. As the world's largest river empties into the Atlantic, it dumps over 200,000 cubic meters of freshwater every second. This massive freshwater plume pushes hundreds of kilometers into the ocean, carrying silt, organic material, and nutrients that give the water a muddy, brown hue. The contrast between this river discharge and the clear, blue ocean water creates a jaw-dropping visual effect that looks like a collision of two worlds. And we can't forget the Indian Ocean-Atlantic divide near the southern tip of Africa. This region, known as the Agulhas Current System, creates a swirl of eddies and temperature boundaries as warm Indian Ocean waters spin back into the cooler Atlantic. The clash of currents and water properties forms visible boundaries, especially when viewed from space. These oceanic borders aren't static. They move with the seasons, driven by weather, winds, and shifts in the Earth's climate system. But every now and then, conditions align, and for a brief moment the ocean draws a line that captures imaginations around the world. These are nature's watermarks, powerful reminders that the ocean is not a single uniform entity, but a collection of living, moving systems constantly in tension, harmony, and evolution. At first glance, it seems like an invisible wall keeps the Pacific and Atlantic Oceans apart. The contrast is so sharp, it feels like you could dip your hand in and feel the edge. But the real story is much more complex and much more fascinating. The line you see on the surface is real, but it's not fixed. It's not a barrier in the way a wall or dam would be. It's a gradient, a boundary where two different water masses are slowly but surely blending together. And that process is happening on multiple levels, from the microscopic to the massive. On a molecular level, diffusion is constantly at work. Water molecules don't recognize borders. When saltier water meets fresher water or warmer water meets colder water, the molecules begin to interact, exchanging heat, mixing ions, slowly evening out the differences. But because ocean volumes are so immense and conditions like temperature and density push against mixing, this process takes time, lots of time. Above this microscopic mixing, there's turbulence. the churning of the sea driven by wind, tides, and waves. This turbulence adds energy to the water, increasing mixing at the boundary. Imagine stirring a cup of coffee with cream. At first, you see swirls and layers. Then, over time, it blends into one consistent color. The oceans are like that, but on a scale so massive, we sometimes see the swirls stretch for kilometers. Then there's subduction, a process where denser water from one ocean slips under the lighter water of another. This happens often when colder, saltier water meets warmer, fresher layers. Subduction forms underwater rivers and stratified layers that can remain separated for months or even years, moving silently beneath the surface while maintaining their distinct identities. Satellites help us see this from space. What looks like a clear border from above is actually the result of light reflecting differently off varying water densities, colors, and particulate levels. Underwater, the boundary is less obvious, but still present. This subtle separation has powerful effects. It can steer marine animals, some of which follow these boundaries during migration. It affects nutrient flow, oxygen levels, and even weather patterns above. In some regions, these boundaries form temporary barriers to pollution, preventing oil spills or other contaminants from spreading as fast, though eventually everything finds a way to mix. So yes, these waters do mix. But the illusion of separation is a fleeting visual created by immense and intricate forces playing out in slow motion. It's a reminder of just how alive and dynamic our planet is. The ocean isn't divided, it's dancing. When we talk about the layers in the ocean, whether caused by temperature, salinity, or density, we're not just observing a scientific curiosity. These natural boundaries have real, tangible effects on the environment, marine life, and even human activity. The ocean's ability to layer itself isn't just fascinating, it's essential to life on Earth. Let's start with marine ecosystems. Stratification plays a vital role in where marine species live, feed, and migrate. Some fish and plankton rely on specific layers, warmer or cooler, more or less salty, to survive. Certain nutrients stay trapped in deeper layers, while oxygen-rich water hovers above. When the boundary between them is too stable, it can block nutrient cycling, starving the surface layers of vital minerals that feed phytoplankton, the base of the entire marine food chain. In regions where stratification is strong and mixing is weak, such as the tropical oceans or the Black Sea, the deep water becomes oxygen-deprived. Without oxygen, these zones become inhospitable for most marine life. Scientists call them dead zones, vast regions where fish cannot survive. These zones are increasing with climate change, and their formation is tightly linked to persistent ocean layering. Next, there's the impact on global climate and weather systems. The ocean is Earth's largest heat reservoir. It stores and transports heat around the planet through currents like the Gulf Stream or the Antarctic Circumpolar Current. When oceans are heavily stratified, heat exchange becomes less efficient. The result? More intense weather patterns, like prolonged droughts or stronger storms, as the ocean struggles to breathe and regulate the atmosphere. Ocean layering also affects carbon cycling. The ocean absorbs about a quarter of the carbon dioxide we emit. But when surface layers become too warm and isolated, they absorb less CO2, leaving more of it in the atmosphere and accelerating global warming. It's a feedback loop, and stratification is at its core. Even shipping and navigation are impacted. Changes in water density can affect buoyancy, sonar readings, and submarine operations. In naval strategy, understanding the boundaries between ocean layers can mean the difference between detection and stealth. For commercial ships, temperature gradients can influence fuel efficiency and route planning. And then there's the human connection. Coastal communities, fisheries, and tourism industries all depend on a predictable, balanced ocean. When stratification disrupts that balance by limiting fish stocks, altering water clarity, or changing local climates, it impacts livelihoods around the world. In short, the line in the water isn't just a pretty picture or viral video. It's a reflection of deep, powerful forces. Forces that shape everything from the food we eat to the air we breathe. Ocean layering is one of nature's quiet architects, silently sculpting the rhythms of life on our planet. Let's imagine for a moment that the myth was true, that the Pacific and Atlantic Oceans never mixed, not just for minutes or days, but permanently. Two colossal bodies of water, locked in eternal opposition, each refusing to yield to the other. At first, it might sound like a fascinating balance of nature, but the consequences would be devastating. First, the ocean's role in regulating global climate would collapse. Right now, the mixing of ocean currents, especially where different oceans meet, drives the global conveyor belt known as thermohaline circulation. This massive system transports heat from the tropics toward the poles and brings cold, nutrient-rich water back to the equator. If the Pacific and Atlantic couldn't exchange water, that circulation would stall. The result? Europe could plunge into colder winters. Monsoon patterns across Asia could shift, and entire agricultural zones might become unrecognizable. Then there's the impact on marine biodiversity. Mixing zones are ecological hotspots, places where nutrients rise from the deep to support blooms of plankton, which feed fish, which feed everything else. If the oceans couldn't mix, the Atlantic and Pacific would become chemically isolated. Some areas would become nutrient deserts, while others might become too toxic or oxygen-starved to support life. Fish populations would crash, coral reefs would bleach and die. Entire marine ecosystems would collapse, and it wouldn't stop at the sea. Remember, oceans absorb carbon dioxide from the atmosphere. Without mixing, surface layers would quickly become saturated, unable to absorb more. That means more CO2 staying in the air, speeding up climate change. Weather would become more extreme, coastlines more unstable, and food systems more unpredictable. Even economically, the effects would be catastrophic. Commercial fishing would decline. Shipping routes would need to adapt to new patterns of wind and current. Coastal cities would face accelerated sea level rise without the stabilizing effect of ocean-driven climate regulation. It's a domino effect. The longer the oceans stayed apart, the more the Earth would tip out of balance. Thankfully, that's not our reality. The oceans do mix, slowly, dynamically, and with incredible complexity. It's that very interaction, sometimes invisible, sometimes dramatic, that keeps our planet alive and balanced. So the next time someone tells you the oceans never mix, remember this: if they truly didn't, we wouldn't be here to argue about it. So do the Pacific and Atlantic Oceans meet but never mix? Not quite. What you've seen, those sharp lines dividing the sea, are real, but they're not what they seem. There's no invisible wall, no magical boundary, just physics, chemistry, and scale, working together to create a breathtaking illusion. Oceans do mix, but they do it slowly, through layers, currents, and forces that span thousands of miles and years of time. The real beauty here isn't in the myth, it's in the science. Because understanding how and why these waters interact tells us something deeper about our planet, about balance, flow, and the systems that keep Earth alive. It's a story of separation, yes, but also one of connection. Two great oceans, not locked in conflict, but engaged in a quiet, powerful dance that shapes our weather, nourishes our seas, and sustains life as we know it. So the next time you see that famous video, the one where the oceans seem to collide but not combine, you'll know the truth, you'll see the science, and hopefully, you'll feel just a little more awe for the planet we call home. If you enjoyed this deep dive, don't forget to like, comment your thoughts, and subscribe for more mind-blowing stories that bring science and nature to life.